Bismillahirrahmanirrahim. Welcome to the course on FPGA based system design. So the course is about just a short. If I want to describe in a very short terms or sentence, I will say it is about algorithms to hardware mapping, and the type of hardware that we are talking about in particular is FPGA, which stands for Field Programmable Gate Arrays. So FPGA is a very interesting kind of implementation platform which can be used to implement any digital circuit. Okay, so any circuit that you have studied in your DLD course, you can implement it on FPGA. It can be as simple as a adder, or it can be as complex as a full microprocessor. So you have that kind of power and that kind of computational resource at your hand. Initially, FPGAs were used as a prototyping devices by semiconductor companies. For example, if Intel wants to implement its Intel Core i5 processor, maybe Intel wants to first check if the processor is okay, it is free of all the bugs. So in that case, Intel will first implement the microprocessor on an FPGA, and it will check it exhaustively to see if it works. Then if they are satisfied, they would go from an FPGA implementation to an ASIC implementation. Okay, so it may be the next step. FPGA can be used for prototyping, then you can go to ASIC. But with time, the FPGAs have become so much powerful that nowadays people just implement their system on an FPGA and put it in their application. So nowadays mostly they are not used for prototyping, but they are used for actual implementation of the system. Okay, so as a first thing, we want to start the FPGA architecture. So by architecture we mean how the FPGA is constructed, because as electronic engineers, you know about the electronic circuits, so you may be interested in knowing how the transistors are combined to form an FPGA. Okay, so in order to understand, let us start by taking some example of combinational circuit. For example, a half adder. So you know very well, a half adder is this kind of circuit which has two inputs, A and B, and it has two outputs, sum and carry. And if you want to more specifically define a half adder, it is defined by a truth table. So we can completely specify the half adder by a truth table for sum output and a truth table for carry output. So you see, we need two truth tables because there are two outputs. Now, given this kind of combinational logic, what we are interested in a very generic, let's say, universal gate, which can implement any combinational logic. And that universal gate, it's not actually a gate, but I want to make you understand, so I am calling it a universal gate. That is called a lookup table, or for short LUT. So a LUT is a device, or more specifically, it is a very small memory, okay, which can implement any combinational circuit. Implements any combinational logic, okay. But there are some constraints. So the first constraint is on the, for example, if this is our lookup table, okay, this is just a box, and this box may have 3 inputs, okay, and it may have 1 output. So this may be O, and this may be I0, I1, I2. So this is called a 3 LUT, or 3 input LUT. Now a 3 input LUT can implement any function that has 3 inputs and 1 output, okay. It can be any function that you can think of. So if we have this circuit and we want to implement it on a lookup table, what we need at least a lookup table which has 2 inputs. So input A, input B are connected to the inputs of LUTs. So this may be our I0, and this may be our input I1. So what I'm saying is we have a LUT which has 2 inputs, I0 and another input I1, and we have 1 output, let's call it O. So you see that A is connected to I0, B is connected to I1, and the truth table, you see, this goes into the memory cells of a lookup table. So a 2 input lookup table, so if it's a 2 input lookup table, it has 4 memory cells. So every one of these boxes is an SRAM cell, and you know very well from your previous course on VLSI circuits that an SRAM cell can store a single bit, and you also studied the transistor level circuit for the SRAM cell. So lookup table is nothing else than a combination of SRAM cells in which we can store the truth table. So how it implements the truth table: the first cell has an address of 0, 0, the second cell has an address of 0, 1, the third cell has an address of 1, 0, and the fourth cell has an address of 1, 1. So this becomes our address 0, this becomes our address 1, 2, and 3, and we just store. On 0 location we store a 0, on 1 location we store a 1, on second location we store another 1, and on 4th location we store a 0. So this is how we implement the sum bit of a half adder. And similarly, we can take the truth table of a carry and we can just store it on the location. So these are our locations, and on every location we store the bits, and we call this the lookup table for carry. So you see, this is a very easy method. If I want to implement, for example, a 2 input OR gate, what will be the lookup table contents? Okay, so it will be like this, that this is 2 input OR gate. I can very easily do something like this, that I will say this location is our 0 location. So I store a 1 there, I store a 1 there, sorry, so on a 0 location I store a 0, on a 1 0 location I store a 1, and on 1 1 I store a 1. So whenever my A and B, which are connected, for example here, so this is I0, this is I1, whenever my I0 and I1 are 0 0, the output is 0, so this is my output, okay. And when it is 0 1, it is 1, when it is 1 0, it is 1, when it is 1 1, it is 1. So this is how I implement a 2-input OR gate. You can also think of how to implement a 2-input NAND gate, for example. So this is interesting. Now we have a very generic universal kind of gate which can implement any function. Just increase, if I want to implement, for example, a 5-input function, I need a 5-input lookup table. If I want to implement a 6-input function, I need a 6-input lookup table, okay. So again, this is the repetition of it, but sometimes we can do interesting things, like for example, we in the previous slide we use 2 outputs. Sometimes we can combine the output, the 2 lookup tables into one. For example, this can be a single lookup table which has 2 outputs, okay. So it is a lookup table which has 2 inputs and it has 2 outputs. So the output commonly use the same inputs. This is the constraint. If the inputs are the same, then the 2 lookup tables can be merged and we can have a lookup table which has more than 1 output. So this is also interesting, and this is widely used in commercial FPGAs. So in Xilinx FPGAs, we will see in the upcoming slides that they have 2 outputs. Now let's come to a bigger circuit, which is a full adder. Again, this is a combinational circuit, and the truth table is, this is the circuit which is well known to you from your digital logic design course. It has 3 inputs, A, B, C, N, and it has 2 outputs, sum and Cout. And if we talk about the truth table, so this is the truth table. We have 3 inputs and we have 2 outputs, and we can very easily implement it on a 3 input and 2 output lookup table. And what we need to do, we need to store these 2 columns. Okay, we need to store these 2 columns here at the corresponding address. So on 0 0 0, which is our first address, we store 0 0. If, let me take another address, for example 0 1 1, so this is location number 0 1 2 3, this is 0 1 2 3, and you see on the third location we have a 0 1. Okay, so it's very easy to implement any combinational logic. You just take the truth table and put it inside your SRAM cells of the lookup table. So that is very interesting. And now in commercial FPGAs, the lookup table is implemented in a way that it can be configured to multiple functions. So let's take the circuit in A. So if we see, we have these configuration cells here, which is called SRAM cell, So in the first cell we have a 0, okay, in the next cell we have a 1, then in the F cell, which is the 16th input, so basically this is a 4 input LUT, k is equal to 4. So if it's a 4 input LUT, how many SRAM cells we have? We have 2 raised to the power 4, 16 SRAM cells. So you see, this is SRAM cell 0, this is SRAM cell 1, and this is SRAM cell number 15. That's why it's denoted by F. And a lookup table is nothing more than SRAM cells combined with a 16 cross 1 mux. So you see, the select lines of the mux are basically your address line. So this is my address line A0, A1, A2 and A3. Previously I was calling it I0, I0, I1, I2, I3. Now I am calling it A0, A1, A2, A3. It doesn't make any difference. And here the output is called, for example, L. So you see, this is a 16 cross 1 mux, and if I gave it an address of 0, 0, 0, 0, so the SRAM cell 0 is selected. If I gave it, for example, 0, 0, 0, 1, so SRAM cell number 8 will be selected, and your function is stored in the SRAM cells like we discussed before. Now on the output is some other logic, which is if you want to implement a register or a flip-flop that is connected to the output of your lookup table, you can very easily do it. So it depends that if you want the flip-flop to be activated, you just put, for example, in this mux, here is the select line is 0 and here the select line is 1. So you just need to program this mux with a 0, which will select the output of LUT and it will be passed to a flip-flop. So you can store the output of a flip-flop for 1 clock cycle if you configure the SRAM cell here with a 0, for example. So this is how you implement a combinational logic. Interestingly, there is another kind of functionality that you can achieve with the lookup table structure. Now this lookup table structure is actually implemented by Xilinx, and this is from this paper. Sorry, this is a book, partial reconfiguration on FPGAs, architecture, tools and applications, published by Springer in 2013. So this is from that book. And the second functionality that you can achieve with the lookup table is that you can implement a shift register with the lookup table. Just to remind you, a shift register is something like this, that you have multiple flip-flops and the output of one flip-flop is connected. So this is our N and this is our out. So if you put something, for example, a 1 here, it will come in one cycle here, another cycle here, another cycle here. So this is a shift register. So this is one important sequential circuits which we studied at the end of our VLSI course, if you remember. And you can very easily do it with this kind of connection. So you just need to connect the output of one SRAM cell to the next one, and then the output of this SRAM cell to next one, and then the output of this SRAM cell to next one. And remember that all of these SRAM cells are clocked. So on every clock, if you put something in the first one, it will go here. In the second cycle, it will go here, and you can form a chain of these flip-flops. So the lookup tables are implemented in Xilinx FPGAs. They can implement a shift register. Sometimes they are called SRLs. These shift register in Xilinx language, they are called SRLs. Okay. The other functionality, the third functionality. So this one was combinational logic. This is sequential logic, and this is again a sequential logic. Okay, so these are three different kinds of applications of the same circuit. So the third application is what is called LUT RAM. Okay, lookup table RAM. And this application is that you can implement a small sequential memory. Remember, sequential memory. Okay, in the first case, the memory is not sequential, it is combinational. But in this one, it is sequential. Okay, you see that there is this very important signal dn. This dn is not present in the first case, and this dn is basically accessible to user when LUTs are used in LUT RAM mode. But when LUTs are used in combinational mode, the dn is not visible to the user. Okay, so the user cannot modify the contents of these SRAM cells in runtime. So you should be very clear in the difference. In LUT RAM, the contents of SRAM cells can be modified in runtime while the FPGA is running. But in the first case, the contents of SRAM cells cannot be modified in runtime. They can only be modified when the bit stream is downloaded in the case number 1. Okay, but in case number 2, they can be modified in the runtime. And how it is achieved is through some more circuitry that is here. So we have a 4x1 decoder, and this 4x1 decoder has these address lines W0, W1, W2, W3. So if you want to modify the contents of the first SRAM cell, you have to put W0 is equal to 0, W1 is equal to 0, W2 is equal to 0, and W3 is equal to 0. And then you can write your desired value on dn, and it will be modified. Similarly, if you want to modify location number 15, you just need W1, W2, W2, W3 to be 1, 1, 1, 1. And you can apply the value on dn, and it will be modified. Okay, so this is how the lookup table can be used in memory mode. So these are very interesting and very important 3 modes in which lookup table can be used. So these are called operational modes. I hope that it will be clear to you. Now let's come to the transistor level implementation. So in the previous slide, we showed basically that a lookup table is a combination of SRAM cells and a 16x1 mux. But actually you can visualize it more clearly as this kind of transistor structure. So basically this is mux at transistor level. So this is just a portion of the 16x1 mux, and I hope that you can now analyze how this works. That, for example, if A0 is equal to 0, so all these transistors in the first level will be on, but depending on A1, some of the transistors may be off and some may be on. No, sorry, in the first level we have, if it is 0, so it means that this one will be on, this one will be on, this one will be on, and this one will be on. So all the even numbers will be on and the odd numbers will be off. Same goes in the next level and in the next level, and you can figure out how it works at the transistor level. Similarly, on the left hand side, this is again from your VLSI course. This is the transistor level circuit of a SRAM cell. So I do not need to go into the details of these circuits. Now, as I told you before, that in practical commercial FPGAs, we have lookup tables which have more than 2 inputs. So, for example, in Xilinx 7 series FPGAs, all the lookup tables are 6 input and 2 output. So the lookup tables have 6 inputs and 2 outputs. And interestingly, this is a very interesting combination, because it means that you can implement any 6 input function or 2 5 input functions. Because how it is organized is like this, that inside a 6 let or 6 input let, we have 2 5 input lookup tables. So the first lookup table has 5 inputs and the second lookup table have 5 inputs. Call them A1, A2, A3, A4, A5, A1, A2, A3, A4, A5, and they are shorted. So these are our 5 inputs. And the 6th input is doing something interesting. It is connected to the select line of a 2x1 mux. Okay. So if you want to use it in a 6x1 mode, which means that you implement all the 6 variables for a single function, then what you can do is, for example, if this is 0 and this is 1, okay, so in 6x1 mode, A6 is variable and in user control. So for example, when A0 is 0, this first lookup table is selected, and when it is 1, the second lookup table is selected and routed to O6. So in 6x1 mode, we have only one output, and that output is O6. Okay, while in 5x2 mode, which means that we implement 2 functions on the lookup table. Each function has 5 inputs, A1 to A5, and we have 2 outputs. In that case, the constraint is that A6 is permanently constant and it is held to 1. And important is not user controlled. Then in this case, not user controlled. It is controlled through the configuration bit stream. Okay. So in that case, A6 is permanently 1 and both O6 and O5 outputs are active. So the output of first LUT is achieved through O6 and the other one is through O5. Okay, so this is how it works. What if you need more than 6 inputs? So in case if you need 7 input LUT or you need 8 input LUT. So this is the picture of Xilinx CLB. CLB stands for configurable logic block. So the FPGA has a large number of configurable logic block, and each configurable logic block contains lookup tables. So we have 4 lookup tables, 1, 2, 3 and 4 lookup tables inside a configurable logic block. And then we have some other functionality here, which I will not discuss now but in the coming slides. But I want to focus on this green eclipse type of figure, which has these muxes. So as we have seen in the previous slide, that if we want to implement higher input lookup tables, we can use a mux. So this mux, this one, let me call this a mux. This is also a mux. So these a muxes are called F7 mux. Okay, and what they do, they simply do this. We have our 6 LUT, okay, A1 to A6, A1 to A6. We put F7 mux, okay, and control this with A7, and this becomes our 7 input mux. Similarly, if we combine 2 of these with this B kind of mux, this becomes F8. This becomes 8 input lookup table. So if we say we can implement 4 6 input LUTs in a CLB, or we can implement 2 7 input LUTs in a CLB, or we can implement a single 8 input lookup table in a CLB. Okay, so this is depend upon your needs. So 8 input LUT is huge, and most of the application uses lookup tables that are less than 6 input. So if we consider the practical circuits, most of the lookup tables will be 6 input or below 6 input. That's why these companies did a lot of research on the circuits. For example, the circuits from DSP and control and all these, they looked into these different kinds of circuits, and they checked how many of these circuits, for example FFT or FIR or something like codec algorithm, they looked into these different kinds of algorithms, and they noted how many algorithms required 8 input LUTs, how many algorithms required 7 input LUTs, how many algorithms required 6 input LUTs, and they come to their conclusion that 6 input LUT is enough for most of the applications. That's why a CLB consists of 6 input LUTs, but if your application demands higher number of LUT inputs, you can combine it with certain features, for example the F7 mux or the F8 mux. So you should be clear what that means. So here are some questions. Why aren't the FPGAs just a big lookup table? So you see, the number of SRAM cells is directly proportional to the number of inputs. If we have 8 inputs, we will need 256 SRAM cells, and then we will need 256 cross 1 mux inside it. So it becomes huge. Okay, so that's why it's not good to use a large mux. Instead, smaller, larger lookup table. Instead, smaller lookup tables are better, because you will have more functions mapped to them, and your complexity or your number of transistors in the FPGA, they will be small. Okay, so number of SRAM bits in a lit are basically 2 raised to the power I, which is your input multiplied by the number of outputs. So if we have a single output, or if we have 2 outputs, then it will be multiplied. So for example, for 64 input combinational logic with 1 output, it will be required 2 raised to the power 64 SRAM cells, which is 1.84 multiplied by 10 raised to the power 19. This is huge. Okay, so clearly it's not feasible to use large LITs. Okay, and that's why FPGAs have smaller lookup tables. Okay, so how then we map circuits onto these lookup tables? So imagine we have a big circuit like this one. Okay, this circuit has how many inputs? It has input, for example, let me call this input A, B, C, D, E, F, G, H, I. Okay, so these are the inputs, and how many outputs? It has just a single output, call it O. Okay, so imagine that we have only 3 input LUT, 3 input and 2 output LUTs. Okay, so we have our FPGA with this kind of lookup tables. It has 3 inputs and it has 2 outputs. Then what we need to do, we need to partition this circuit, partition our circuit into a feasible structure that has the number of inputs less than 1. So for example, this is my first partition, and if I look to it, it has inputs A, input B, input C. So okay, I can attach A here, attach B here, attach C here, and it has 2 outputs. Let's call this W1 and W2. So I can attach W1 here and W2 here. Okay, so maybe I call this LUT number 1. Similarly, I can combine these gates and call this LUT2. Similarly, I can combine these gates and call them LUT3. Similarly, I can combine these LUTs and call them LUT4. Similarly, I can combine these LUTs and call this LUT number 5. And I can combine this single one and call this LUT6. Okay, so you see, nowhere in these in circle circuit pieces, every encircled circuit piece should have 3 inputs. So for example, if I check, this is 1 input, 2 input, 3 input. Okay, this one has 2, but it is less than 3. So you can have less than 3 inputs, but you can never have more than 3 inputs. Okay, so this is how we partition our structure of the circuit into lookup table. So this process is called basically tech mapping, or simply mapping, technology mapping or mapping. So you take your DLD circuit and you divide it into small pieces so that each piece can be put into a lookup table. And this kind of process is automatically done by the softwares from vendors. For example, the Xilinx ISC or Xilinx Vivado will automatically do this kind of mapping for this for you. Unless you are a researcher and you want to control this process and you are interested in the software side of electronic design and you want to develop your own technology mapper, then you can play around with this process and develop your own algorithms for this. So so this is how basically it works. So if the circuit is large, you divide it into smaller pieces, and each piece should be such that it can be housed in your lookup table. If you have less than the maximum number of inputs, for example, your circuit has 2 inputs, then one of your lookup table input is unused, and you can deal with it by appropriately configuring your lookup table. So one thing to note about lookup table is that it is only constrained by the number of inputs and number of outputs. So it does not matter that the circuit that you put inside is consisting of 1 gate or 100,000 gates. It doesn't matter. What this means is that if you put a single gate like this one here, or you put, for example, this one, as long as the inputs are 3, which are these, and the output is 1, it doesn't matter. So it is irrelevant to think of lookup table as something that can in terms of the gates. Instead, it only deals with the primary inputs and primary outputs of the piece of circuit that you want to map onto the lookup table. So this is all about lookup tables and how they are implemented at the circuit level, how they operates in different modes, how they can be used in single output mode, how they can be used in dual output modes. All this stuff is very fundamental and very, very important for the understanding of, we can call it the workhorse of FPGA. So lookup table is the workhorse. It is the basic method, a basic logic, basic way for FPGAs to implement combinational circuit. And the material that we covered until now is very, very important to understand if you want to understand the FPGA architecture and its working.